Okay, suppose I have this object on this ramp and it's angled at some angle. Doesn't really matter what it is. Let's just say it's theta. Okay. So the first question is, if there's no friction, what are the forces on this object? And you can imagine what would happen if I take that object and let go. It's going to accelerate down the ramp. Okay, so this is a great example to practice drawing forces on a diagram. So there's two kinds of forces. There's long range and contact. So long range forces are forces for things that don't actually have to touch. In this case, what is this interacting with that it doesn't have to touch to interact with? And the answer is the Earth. There's a gravitational interaction between this object and the Earth. So really, in situations like this, probably the only long-range force that you're going to have is the gravitational force. So the gravitational force depends on the gravitational field, G, 0, negative 9.80 newtons per kilogram, where F, we'll call it Fg, is the mass of the object times the gravitational field. And so it's pointed towards the center of the Earth. In this case, that would be down. So let me go ahead and draw that force in there. So let me draw that off to the side. No, I'll draw it right here. So there's my mg. Okay, now contact forces. So the other things that are interacting with the object have to be touching it. And again, quote touching, if you want to get really all crazy here, you could say, well, nothing really touches because the atoms don't touch. And yeah, I get that. That's funny. Okay, but let's just say in the practical sense of touching, what's touching the object right here? And the answer is the ramp. So if there's no friction, the ramp will only exert a force perpendicular to the ramp. And we call this the normal force. So I'll draw that right here. Now, the normal force is a contact force. There's no straight out equation for it because it can push as much as it needs to in order to prevent the block from going through the ramp. And that's it. Those are my only two forces. Now, if the block's going to accelerate down, we would want to pick a xy axis in the direction of the acceleration. So if I pick this as my x and y axis, that will work. But the only problem is I would have an acceleration that's in both the x and the y direction. So one of the things we do is to say, okay, here's my x and here's my y. That way I have an acceleration in the x direction. But in this case, I want to look at a different situation. I don't want to look at acceleration. I, in fact, want to consider what would happen if I pull with the force this way to prevent it from moving. Okay, so now I have an extra force that I can actually measure. We'll call this just F. And I can measure that. So now I can look at the forces on this object and say the net force is 0. It's not accelerating, so F net, the vector, is equal to mass times the acceleration of 0, so that's the 0 vector. So the forces have to add up to 0, so I can write that as N plus mg plus F equals 0, the 0 vector. Okay. Now, these are vectors, right? And it's a lot easier to deal with these in the x and the y direction. So I could also write this as the following two equations. F net x, what forces are in the x direction? Well, I have this force F in the negative x direction, so it's negative F, plus I'm going to write this as mgx. And that's the x component of the gravitational force. And then the y equation I could write is F net y equals, well, this is in the y direction, so it's going to be n, and this is going to be, part of this is in the x direction, the y direction, so minus mgy. So, but I want to focus on this equation because I can actually measure, I could put a spring right here and measure this force as I change this angle. So one of the things that we can see is that if I draw this triangle right here, this triangle, if you do a little algebra, geometry, I'll let you play with it yourself. If this angle is theta, that angle is also theta. So let me just draw this gravitational force down here. Here is my y-axis. Here's my mg vector. That angle is theta. This angle, right, that component right there is my x component of the gravitational force. So if I say sine of theta is equal to mgx, opposite over hypotenuse, over mg, the magnitude of that, then I can solve for mgx. mgx is going to be mg, sine of theta. So up here, this equation, if I measure that force, it doesn't tell me the weight, it tells me the component of the gravitational force. So I'd say F is equal to, and that's what I measure, mg sine theta. So let's just imagine this to the extremes. What if I lower this down to 0? How much would I have to hold it to be there? Well, I wouldn't have to hold it at all. I wouldn't have to pull it. It would stay there. And in fact, if I put in 0 for sine of theta, I get 0. Okay. What if I let this go completely vertical? Well, then the weight would be, I would just be holding the mass up, right? So if I put in 90 degrees here, I get sine of 90 is 1, and I get F equals mg. So you'd have to support that with the weight. What if I increase this even more? What if I increase this past 90 degrees? Well, I can't have sine of theta greater than 1. So the force can't be greater than 1. And in fact, this is a weird situation because it wouldn't even be pushing on the ramp. It'd just be hanging down there anyway. So, okay, that's a quick introduction to forces on an inclined plane without friction.